Welcome to my demo of a prototype generative music system. Just to explain what's on the screen here, on the left we have our software synthesizer we're using to generate the music sounds. It's an open source software synthesizer called Zin Add Sub FX. It's been around a number of years. It's got some really nice sounds, which is why I'm using it. This is the mixer here, which shows the patch that we're using and the channels. We're using a number of different sounds layered together to create some sounds, and you can hear that through here if we just use a virtual keyboard. Okay, and over here, this is a generative music system here. I've got two types, one's generative and one's random. We'll talk about the generative one first. It's based on a hidden Markov model, what's called Markov model generation. It uses a database of seed compositions, and it auto-generates new music compositions from those seed compositions. And they're different every time they're generated. So there's an element of randomness, but also some sense of structure and playing quality. It's not completely random as this other one that I'll show afterwards is here. So if you think something as opposed to a composed piece of music versus a wind chime is a good way of thinking about it. So the controls here for this generative one, we have the tempo that we want to play it at. Currently we're playing it quite slow. The size indicates the number of notes that we're going to generate each time it does a run through. So in this case we're just doing a short generation because I want to show you how it generates them. This starts and stops it. If we show here, this actually shows the notes that are generated, and we have here in this composition we can look at the notes by their duration, by their pitch, by their amplitude, which is volume, and the hold time, which are the 4 dimensions of MIDI notes that are generated. And this is the seed song that we're selecting here. I'm going to hold that current song. And there's a number of things from the database of songs. We can select songs based on a different type of mood, or we can select them on a style, or we can select them on a key, or a key type, major or minor, and different types of where they're from. And we can control different types. We can play a selected song and hold that song, or we can do a random song selection based on these parameters, play random from different filters. We have some filters down here. So let's just hear what this one sounds like. This is a composition called Koto, and it's a short generation of 34 notes, and you'll see when I hit the start button that it will generate a new sequence, and this graph will change here of the notes. And now we're going to play through these. We'll see the play line come across here. This is the playhead moving through. And we'll see when we get to here, it'll generate a new sequence. And it will sound different. There you go. And you can see this sequence repeated from before. The way, if you know how Markov models work, basically weighted selection of conditional note probabilities of a map that's built from a previous composition. And we'll play this through again, and then I'll just extend the length and you can see more. Look at duration. Okay, pitch. Let's increase for the next one. We'll take it up to 100 notes. That's the pitch contour of the composition currently playing, and we'll see that change with the next one. Oh, it auto resets there. I'll just look at the pitch. So you can see that's a different pitch contour of 101 note composition there. And that's essentially how it works. We can pull that off there, and then we can say, let's play a random song from the filters, in this case here. So if we stop it, it'll start a new one. Let's take it back to a short sequence of notes. You can see here we're playing a new song here, and it's generated a new composition, Fuchsia 1, from this seed song here. When we get to here, it'll randomly select a new song and auto-generate a new sequence of 34 notes from that seed composition. So you can see it's selected a new song there and created a new one. And maybe we want to lock it to a new, let's just select the style of meditative. We only want to select meditative songs in a minor key. And it will show those here. Okay, these are all the songs that are meditative in a minor key from the database of songs that we have. It's selecting a new one from that selection there. So that's essentially how an example of a hidden Markov model with some bells and whistles added onto it to generate new music compositions around some seed compositions of pre-composed music. So you get the benefits of randomness, but you get some order and you get some quality music. So this section here will look at the random generation of music, but we're going to use some different algorithms varying from completely random, emulating a wind chime being blown about in the wind, through to some more stochastic noise generators that vary the randomness through pattern generation. So there's some repeatability in the nature of the notes that they can generate, but there's randomness in there as well. So the first one we look at is the wind chime emulator. And like, if you know most wind chimes, they have anywhere from 5 to 7 sound generators hanging from some sort of framework. Sound generators can be bits of pottery, tin, tuned pieces of pipe, and they can make atonal music, or they can be based on scales. And in this case, we're emulating one based on a natural minor scale and number of 7 scale notes. We're going to start at the note C5, which is in the mid-range, somewhere around there, I think. And the note dynamics here is the dynamic range of the notes that are generated. 91 means we've got a fairly good range from very low notes up to high notes. The note density is how busy it is, so that can be thought of as an indicator of the strength of the wind. So low density is very much a low breeze. So you'll get a small number of notes generated per second, and a high rate up here would be a very windy type of environment. And the note length is how long each note can be held for. That would be a sense of the decay, depending on in real life it would be based on the type of material that the sound generators are made from, the density of the material, how long, when they strike each other, how long the sound decays. So let's just see what that one, and we have a little map here that we can see generating, see how the notes are generated, some information on the notes, the algorithm, events per second, and the keys of the notes that are generated in terms of their pitch and their velocity. So let's just look at the first one, which is the wind chime. So this is low density. Imagine it's a low breeze. Take it down even lower. So imagine it's a wind chime that's, you're getting a breeze, not a steady breeze. It's coming through and occasionally blowing the wind chimes. And then we can emulate a stronger breeze. Which you can see down here, density of the notes generated, and then it gets even, so it gets even stronger. You can see down here, low note dynamics, because in a heavy wind, objects will be getting struck quite heavily together, so there would be less dynamic range. And you tend, if you go back to another condition where you've like got a medium type breeze, you would have quite a high dynamic range because the variability between the sound generators being struck could vary quite a lot between just touching each other and then bashing into each other quite heavily. And if we just we could change the scale notes, so instead of 7 sound generators, 7 notes, let's say you've got more, so you've got 14 of them. So now we can hear that there's higher pitched notes being generated from that scale. So you can constrain the composition depending on the number of sound generators, pitches that you have. So let's just take that back to 7, put it in 1 octave here. And we look at some of these other generative algorithms here, the random ones. These other ones are using variations of what's called Perlin noise to experiment with getting some sort of repeatable patterns, but also on a random basis. So if we look at turbulence, you can hear straight away there's a difference in the audio output. And you can also see that here if we look closely at the mappings. Turbulence algorithm has a tempo change to it inbuilt into the nature of the algorithm, so it ebbs and flows. Now we're speeding up a bit. No, we haven't changed any of these parameters here. It's doing it automatically through the algorithm. Slowing down. We take the note density down a bit. Let's try another one called improved noise. Immediately we hear a change again in the note generation. And compare that again to the random nature of the bass wind chime. FBM is fractal Brownian motion. Let's take it down another octave from the bass note. And marble. You can see that the noise-based generators have more of a regular note generation feature to them. We add in the layers. And you could use these at various times. You could drive these programmatically and switch between the different algorithms if you map them to emotional states, for example. Let's go back to the random one, using the layers. Let's try a different scale. So you can do quite a lot to vary the sound. So you vary that between different types of generative random algorithms, and then we have, as we saw before, with the other generative algorithm development.